Hello, welcome back after the break. We are starting with the second part of the workshop, the simulation of the capillary pressure curve in the GDL. I am now going to switch back to the cloud. We have all the settings as before. I now change the module to go to the prediction module and I select the module SATUDICT. From here, we have now a drop-down menu with different things that you can calculate. We take the capillary pressure curve and we click on Edit to define all the options. The GUI from the GEODIC 2023 has changed, and I don't know if you know the GEODIC 2022 before, but now we don't have wetting or a non-wetting phase. We have just the invading fluid and a replaced fluid. And the contact angle, CA, is important here. And we start with, you have the invading contact angle and you have the replaced fluid contact angle. In our simulation, we have air inside, and we're going to invade with water coming from the catalyst layer. So we have the water with a contact angle of 40 on the carbon fiber, and the replaced fluid is air. And this one has the contact angle of 140. Together it's 180, and that's, you can see here, it's important to have at the end of 180 to get all the plane again. So you can see it here. We select the constituent materials. ID3 is solid. It's a manual solid in this kind, and we can add catalyst layer as information so we know which kind of role it has. We have the catalyst layer, and here we have also manual material, so we don't need specific material parameters, and we just give the information flow field. We give the information. We have the contact angle. That's now correct. We have the surface tension of 0.07205. The experiment we're going to use is constant contact angle. The experiment is now always in Bevision, and if it's drainage, so forced, you can decide this when you change the contact angle. So here you don't have to do something. We are going to have those check marks here. So the invading fluid must be connected to a reservoir, and the replace fluid can leave a residual. So we allow that. We make a check mark to use dynamic pore morphology. We can also check mark non-monotonic capillary pressure, but this will increase the simulation runtime to a large extent. In this particular case, it won't improve the results. That's why we keep it unchecked for this workshop. But if you have small pores, it is important to use this check mark. You can also read the tooltip to understand what this one is going to do more. At the next point, we are going to look at the boundary condition. So here, it's easier to look here at the structure. The invading fluid inlet. So the invading fluid is coming from -z and it's going to +y. So we are coming from the invading fluid from -z and not from here. So the replaced fluid outlet, so it's coming here, is the water is coming. It's going through the GDL, and then it's going to take the flow field here to leave the flow field. So we have the replaced fluid is in Z plus and Z minus direction. The boundary condition is symmetric at all directions. So we have the fluid coming from minus Z, and it's leaving from minus to plus Z direction. Next step is to go to the solver parameters. We have a step size of pore diameter of 2. We have an interface step size of 64. Here we can choose the parallelization. So it's here the local maximum is 8. It's okay. We can write all GDL. We need a check mark at write pore filling steps to pass, because like this we get a nice output file. And here we can look at the equation that will be solved. And here's also the definition with the contact angle. Normally we would click on OK and then on Run. In this part we do not click on Run because it needs very long. We click on Save Settings to File. And we can click Save the Settings to File, and you can do it later. We are now going to part 1, building cell, to datetime to end, perform SATODICT simulation. We load the SATODICT result file. Here we can click on data visualization. We have here all the structure for the different steps. And we can load all of them together. We click on load. We get the pore filling saturation file. It's a volume field. We now need to load it. And now you get the last step loaded. Oh, needs a second. Was calculating. Okay, now it's the step 0. What you saw before was the last step when all the pores are filled. And what is interesting for us is the intermediate results. So we have now the structure here. We can change the colors for that. It's a little bit better to see. Can make a light gray for the carbon. Can make a dark gray for this. Also make it darker gray. So now it's maybe a little bit better to see. When we have the water, you can now see here that the droplet is coming. You can change also with the settings here of the clipping. You can see here the structure and about how the droplet is changing. To get a nice visualization, you can click on the smooth structure renderer. Need a second maybe to wait. Now you have a little nicer visualization here. If you want to save a specific visualization and want to save the settings for that, we are going to save image as. That's a click on OK, and then we have a saturation structure. Click on save. Now we save the image, and then we can really go to macro, session macro. You here have the settings here and click on save, and now you can save the structure. Now we are going to prepare the structure for the ADDIC simulation. We've been using a slider to see when we want to use the droplet. And we take it when it's a little bit smaller, and we take this as intermediate result. And then we can make the ADDIC simulation to track the particles that start from the surface. Firstly, we have to load an intermediate structure. Because here the droplet is the flow field, so it's not a structure, it's just where the water is. And we load one of the structure that is a part of it. I open again the result viewer. I'm not 100% used to. So here are the different steps. And for all the steps we had now with the flow fields, or with the calculated places, we have the structure together, and we load the structure, and I think the structure 32 should be good. I forgot to decheck the smooth representation. That's why it needs 2 seconds now to load the structure. Normally it's faster. I'm working on the box representation. So now we can see, here is the droplet as material. I can close this one. So we have here the droplet that's coming from the volume field. If I decheck the volume field, we don't see a droplet, so I should maybe take a later structure for the simulation. I always go like here because I want to open Geodict here because I'm used to, and I'm not already used to have it on the top. Go to result viewer, so the step 32 is not enough, so I maybe take the step 35, but now I'm a little bit smarter than before because I go on structure, I go on box, and it will be a little bit faster to load it. I tried again with the 35. So it's some steps later. We see here, oh, that's already a big droplet, so I take it something in between. So I take the 33. Okay, it was one too early to have seen all the different kind of structures. We're going to take the before. So this is the perfect structure, the one we want. So we have it now in violet, the water, the invading water. For that you're not confused too much, we change the color and we make it blue. And to explain Geodict that it's not just allowed to take the surface and that all the particles starting from the surface, we are now going to dilate. That's why we have the process geo already open. And we dilate the material 5, that's the invading water, with a coating material IT7 with 1 voxel. The presetting is 2, so we might change this. Click on OK, and you click on dilate. So I change the color because otherwise we don't recognize the water when it has the same color than the carbon fibers. Now we have the surface with 1 voxel coated. Here we can see it's 1 voxel on the surface. And now we can maybe turn the sides, because here we have to can see it better. and we go to the module Adidict. I will click on Edit. So we have now some parameters open. We firstly go to the time and the time step. If you don't want to enter the parameters yourself, you can also go to take this step and take the Adidict result via drag and drop inside. It's asking if I want to override my current material settings. Click yes. I get here some material ID properties. You normally always get those message when your material ID is not fitting to the one of the result. And as I did it before on my computer, I was using different materials, because you can have here water as the invading fluid. You can also have it on manual. For the simulation, it does not make a difference because there are no material parameters that are relevant, but the constant angle and that's what you put inside. So it does not make a difference in this case. I get a warning to say that some material that I have to check the material properties, and I like the warning. And it also reminds me that sometimes there might be changes, and that the material database from Geodict is a very important point. That's why I let it also have the warning in this user meeting workshop. So we have the properties already inside. So we have the time. We start at a very small time step, so 0.0015 seconds. We take also the small time step, so it's behind this starting time. We have a mean velocity of 5 meters per second. We take the Navier-Stokes simulation. Here we have the when we have the boundary condition in Z, it's wind point. We have no slip length, and the particle boundary condition is reflective to all sides, but the Z plus direction, this is open. The constituent materials we have already been discussed, so we take here water, in fact the water distilled. The non-wetting phase, it's still from, the information is coming from Satidict. We have the particles, we will create particles. So we don't load them, we create them. We create them from a chosen material ID. That's why from the coating, we did before. We take the coating here, it's ID 7. We have a start velocity of 0. We have a particle start time of 0. And we start with 10,000 particles. We have an interaction model of here sieving. We have this interaction model, pass through model. We take sieving to all of them, so not adsorption or caught on first touch. We have a sieving model. And we have a size distribution here where the diffusivity and pore is defined, and it's the same for all of them. The error bound we can make maybe a little bit faster to get a faster result. We can keep those parameters here. We have here 2 check marks. If you want to have something else in this part, you can also do this. Here you can look at the equations. You can click on OK, and I will click on Run. I did the reaction before one time. That's why I click on Override. In fact, I had the wrong setting before. I recorded, that's why I already have this. And while the simulation is running, I think we can make a little break of 10 minutes. See you later, and if there are questions, please ask them. Now it's time. If there's no question and you just wait until simulation is done, you can also take a coffee, for example.